briefly summarize what we did yesterday. So, we talked about Brownian motion. So, it is a free particle, let us say of micron size in water, and we define this object. So, this is the probability that the particle is at position particle is between position x and x plus dx at time t. So, this is a probability, and we showed that it satisfies the equation delta x square, right. And so, where is diffusion coefficient d is given in terms of the temperature and the friction coefficient, right. So, this is the probability of the particle being between x and x plus dx at time t, right. And so, then we also found that, so this is a description in terms of the probabilities. So, this is called the diffusion equation, and in general it is called a Fokker-Planck equation. So, I will just come to the derivation of the general Fokker-Planck equation, I think maybe in the next class. So, now we also showed that you can describe this system in terms of the trajectories of the particles. So, how does it look? So, it is basically this is t and this is x. So, you just let us say it starts at the origin at time t equal to 0, right. So, it has a random trajectory, right. So, it has some stochastic trajectory. So, it looks something like maybe something like that, and this is x at time t, right. So, you can also describe these trajectories in terms of some differential equation, and the differential equation is dx dt is equal to square root of 2d times some noise. So, this is a Gaussian noise. So, it is basically distribution is Gaussian with a mean which is equal to 0 and variance is, so it is uncorrelated in time, right. So, this is what I guess we did in the last class, right. So, now what we are going to do, so we look at this particle, so which satisfies this equation, but under some constraints. Okay. So, one of the interesting questions people ask, for example, so you have some absorber somewhere and these particles are moving, and what is the probability that this particle does not, or the particle does not get absorbed up to some time t, right. So, that is called the survival probability. So, imagine that again you look at this trajectory plot. So, this is t and this is x. So, at x equal to 0 you have put something, and it starts from some position x naught initially, because now if you start from here there is some absorber. So, if you start from here, of course, it cannot move, right, because it just gets absorbed immediately, right. So, you start from here and ask, so how long this particle survive. So, survive means how long this particle stays without crossing this line x equal to 0 line, x equal to 0 point, right. So, basically you are asking what is the probability that this particle goes from somewhere from here to some position x without crossing x equal to 0 point, right. So, this is x equal to 0. So, if it crosses those trajectories, basically dies, the particle dies, right. So, imagine that you have something and these guys are moving, and when, in one dimension, whenever it comes to the origin, this guy gets stuck. So, for example, there might be some trajectories which goes there and then it gets stuck there. So, that is the particle basically is dead at that point, right. So, we want to ask how long this guy survive. So, we define x0 t is the, so this is a probability now. So, this p was a probability density, right, this is a probability. So, this is a probability that particle survives up to time t starting from the initial position x equal to x 0. So, this is at time t equal to 0, right. So, so before that we so what do we have to do? So, basically what contributes to this probability? It contributes, this one comes from all trajectories which does not cross this point, right, x equal to 0 point. So, first we have to find out all those trajectories which does not cross this point, right. So, we can again define a probability density function x t, let us say starting with x 0 at 0. So, this is the probability density function, or if I say this one. So, this is the probability that this particle goes from x 0 to x without crossing this x equal to 0 point, right. So, this is, yeah, so this subscript a I just put it because of absorbing, right. So, what kind of equation this probability density will satisfy, right. So, it will, so this is some probability density, it will satisfy some kind of differential equation. So, what kind of differential equation it will satisfy, right. See, when you derive this differential equation, right. So, these differential equations are local, right. It says okay, it goes from here to here and then we just expand near and we derive that equation, right. So, this is a local equation, but this constraint is something at some point, right. So, if this particle is here, it does not know about this condition, right. So, it does not know that if there is some absorber here or not, if particle is moving somewhere there, right. So, therefore, this must satisfy the same differential equation, right. So, P A satisfies the same equation dt, this is equal to d del 2 P A del x square. P A is the probability, this times dx is the probability that particle goes from x 0 to x, that is the probability density that it goes from x 0 to x without crossing x equal to 0 point, right. Yeah. So, that is dx is a small interval somewhere here basically, right. It basically just, so it is just same as this one, this dx, right. So, this is just the probability density that it goes from x 0 to x, or is just the propagator that it goes from x 0 to x in time t without crossing that origin, right. So, that must satisfy the same equation because these differential equations are derived locally, right. So, this condition that this probability it does not cross this origin must come in the boundary condition, right. So, you can have a same differential equation and have different boundary conditions and it will give you different answers, right. Yeah. 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 At x equal to 0, at x equal to 0, I mean near means how near, there is no other scale. Yeah. So near means what? 1 centimeter, 1 millimeter, 1 micron? No, I mean near means what? Right? At x equal to 0, this does not satisfy. So that is the boundary condition, right. So near means x going to 0. So yeah, there is no lattice, it is a continuous space.
But the equation says that instead of going to particular point x,
Yeah.
it comes from all nearby points, right?
Yes.
But x equal to 0 is like neglected.
But near means what? There is no other scale, right. So it says that this equation, okay, it does not satisfy at x equal to 0, right. Any other point on the positive x is satisfied. It does not satisfy when x going to 0, in the limit x tending to 0 it is not satisfied. That is what you mean by near, right. So in the limit x tending to 0 this equation is not satisfied. So that comes to the boundary condition, right. But all positive x this equation is satisfied, right. So what is the boundary condition? So it depends on all these guys. So at time t equal to 0, so what should happen? So P A x t equal to 0, x 0 0, this is one. Right. So that is just the same as the probability that it just starts from here, right. So now P A x t x 0 is equal to 0 0, this is equal to, so that must be 0. Yeah, so if so that is 0 if x not equal to x 0 basically, right. So it says then if this start from here it cannot reach there, if it is the same point then it is 1, right, because that is the probability that going from here to here, but if that x is also x 0 then it is 1, right, because it is just there at the same point, right. But we are not going to use this boundary condition. So this is the initial condition, and since we are solving with respect to x, this boundary condition basically we need with respect to x, right. So that is just the condition with respect to these initial points. So what is the boundary condition? So boundary condition says x equal to zero at time t x 0 0. So this is equal to, so this is by definition it's 0 because, okay, so that is also by definition it's 0. So it is by definition it's 0 because we are asking for the probability that it goes from here to here without crossing the origin, and this is the point it just crossed the origin, right, it just at the origin, right. So that is equal to 0, and if this point is very far, x goes to infinity. So P A x goes to infinity t x 0 0. So this is again equal to 0 because it is just some probability and it should be well behaved. So it goes to 0, so that is like normalized or something, right. Yeah. So now we need to solve this equation. So let us remove this guy. Using this initial condition and these two boundary conditions, right, and this enough because it is two derivatives in x. So, we need two boundary conditions, there is one derivative in time. So, we need one initial condition, right. So, this is what we are going to solve. So, before solving this equation let me just give you the answer, right, let me just derive the answer in a by some arguments and show that that is the correct solution and you know that, so this kind of equation, if given the initial condition and the boundary condition, it has unique solutions, right. So, if I give you the solution and you can verify that it satisfies everything, that must be the solution, but then we will derive the solution again. Okay. So, let us just try to understand the solution. So, if there is nothing, this condition was not there, so what is the solution? So, that is P, right, P of x t. So, if x t, let us put this one also starting with x 0 0, right. So, if this condition was not there, so that is the probability density. So, what is the answer? So, this answer was 4 pi dt e power minus x minus x 0 whole square by dt, right. So, that was the solution. So, that is what we found yesterday. So, now, so this solution is what? So, that is the solution for the particle going from here to there in time t. So, that includes all trajectories, right. So, if you just think in terms of this probability density, so basically those are the, this contribution comes from all trajectories, right, which goes from this point to this point. So, it is like, so if you just think of it this way, so this is t, this is x, so this is point x 0 and this is x at time t, right. So, this is x, you start from here, so this is one trajectory, this some trajectory might go like that. Okay. So, this is basically x and x plus dx. So, there will be some trajectories which will come, this will go like that, right. So, those are the typical trajectories, right. It just starts from this point and goes for this point, and if you take the contribution of those all trajectories, it gives you this solution, right. What is the probability of this trajectory, what is the probability of this trajectory, what is the probability of this trajectory. If you take the contribution of all, it gives you this one, right. So, this is same as what Abhishek did yesterday in terms of this random walk. So, you want to find out, it starts from some point x equal to 0 and this guy does walk on a lattice. So, this particle moves to left and right with probability half, and then you want to find out what is the probability that at some time step n it is at some position m. So, you want to find out m position n at time step n, right. So, this is let us say m equal to 0, 1, minus 1, minus 2, right. So, you start from here, you want to find out what is the probability, it ends there at time step n, right. So, that contribution came from all trajectories, right. We found out how many ways you can go from here to there, right. So, that gave the combinatorial factor, right, and then we gave the weight for each trajectories. And what was the weight? So, in that case weight was just, so this is the combinatorial factor plus 2 to the power n, because each time it just goes to left and right with probability half. So, for all trajectories it had the same weight, right, but of course, here for all trajectories weights are not same. So, it's you have to do something more, but the idea is same, you just sum over all trajectories according to their weight, right. So, now all these trajectories basically gives rise to this probability. So, now we have to find out this probability. So, that excludes these blue trajectories, right. So, blue trajectories are the one which cross the origin, right. So, we want to find out this probability minus the probability that this guy came like this, right. So, we need to exclude that probability. So, let us find out what are those trajectories. So, let us look at this guy, this blue trajectories. So, this weight of this trajectory is same as, suppose you just put a point here minus x 0, right, and you just look at the mirror image of the trajectory from here to here, all the keeping all the others same. So, you just find out the first point where this trajectory cross, and you just look at the mirror image. So, it will be something like, right, something like that. So, similarly for all trajectories which cross this origin, there will be a conjugate trajectories from minus x naught, right, because all trajectories which goes from minus x naught to x must cross the origin at least once, right. So, therefore, this whatever the blue trajectories, those are the trajectories basically which is the weight of those trajectories are same as the trajectories which goes from minus x naught to x in time t. No, mirror image of this part only up to the first crossing, right. I look at the mirror image of the portion of the trajectories up to the first crossing.
Okay, then how does the trajectory continue? Oh, okay, then it's the same.
Then it says whatever the trajectory, it just goes, you just take the follow the other trajectory, right. So, now, so that means that all these trajectories which goes from here to here, right. So, that those trajectories must cross this point x equals 0 at least once, right, and so those are the trajectories basically which comes from x0 to x by crossing the origin, right. For all trajectories which goes from x0 to x by crossing the origin, there is a 1-to-1 corresponding to a trajectory which goes from minus x to minus x0 to x, right. Is this point clear? Right, it is clear to everybody, right. So, therefore, for this object I just need to take this one and then subtract the probability weight of those trajectories which goes from here to there, right. So, this answer is very simple then. So, what is the answer? So, P A x t x 0 0 is equal to P of x t x 0 0 minus P of x t minus x 0 0, right. So, you can see that it satisfies all the condition. For example, if x equal to 0, these two are same, the weight of if you go somewhere here, these two are same. So, this is equal to 0. Of course, when x goes to infinity, this is equal to 0. So, let us write down the solution explicitly. So, the solution is P A x t x 0 0, this is equal to 1 by 4 pi dt minus x 0 whole square 4 dt minus e power minus plus x 0 whole square 4 dt, right. So, that is the solution. So, it of course satisfies this equation because individually both satisfies this equation, because this solution of this. So, this equation the solution, when if you want to see whether it satisfies or not, it does not depend on the initial condition, right. So, here only the initial condition is there. So, both the terms satisfies this equation. So, their linear combination will also satisfy. So, this if you put x equal to 0, both the terms are same, that is 0, and x equal to infinity, of course, that is both.
So, you have to explicitly say that x is greater than or equal to 0, right? Because
Yeah.
x can also have like less than 0.
So, then you just do it from the other side. There is a, it's a problem is symmetric. So, you can just define that the probability that starting from the initial position, it does not cross the origin, right. So, if you you could have just start from this side, said it, okay, starting from the initial position, what is the probability it does not cross the origin. So, it does not matter if you start from this side or that side, right, because there is symmetry, right. So, now this is done. So, but we have to find this guy. So, what is this object?
The thing is that if you just simply plot this function,
Yeah.
then you also have non-zero values for less than 0, but you have to chop it out artificially.
Yeah. So, this one, so either you define the problem on one side, on the other side, and once you define the problem on one side, whatever the side you define, that you just take this solution for only that side, right. So, once you take only for the positive x side, so you just take this solution only positive x side. But similarly, if you take the, so it is a symmetric this thing, so it does not matter, but once you define the problem on one side, you just take the solution on that side basically. So, now, so what is this object? So, this object is basically it goes from x 0 and it survives. So, basically it says that okay, I do not care where the end point is, right. I want to find out all trajectories which goes from x 0 until time t it does not cross the origin, right. So, then what I have to do, so this object is equal to, I just integrate over the end point p of x t x 0 0, right, because this end point does not matter, right. So, I just integrate over the end point. So, now, so when you integrate over the end point, so I am not going to do the integral, but so this is a integral you know, right, this is Gaussian integral and you can do a Gaussian integral in some limited domain, because if you just do from 0 to infinity, you have to just shift this one. So, this limit will shift, so it will be some Gaussian integral in some domain, and if you do Gaussian integral in domains, what kind of function comes? This error function comes, right. So, this answer is basically, can you see, that is the PA, sorry, that is this guy, yeah. So, if you do this integral, so what you find is that is given by r of x 0 by 4 dt, and okay, if you just define the domain on okay, irrespective of x 0 positive or negative, and you just say that okay, starting with x 0 it does not cross the origin, so that becomes just a mod of x 0, right. But this is the answer. Okay, so now let us we are defining for x 0 positive, so that mod does not matter, okay, but that is the answer. So, this is the answer. So, now okay, let me just yeah. So, what is this error function? So, let me just write down the definition of error function. So, this is left as a homework exercise, basically doing this integral so that this is equal to this, where this definition of error function is basically I think 2 by square root of pi 0 to x e power minus y square dy. Yeah. So, what kind of property it has? When x goes to 0, you can you analyze this? X equal to 0, of course it is 0, right, is equal to 0. At infinity, this is 0 to infinity, and can you do this quickly? What is that integral? That's what is the answer? So, that gives you basically 1 because of that 2 by square root of pi, right. So, this is this thing, but suppose I do not put exactly x equal to 0, but x is very small. So, let us so what is the r of x for small x, how does it behave? So, I need to analyze this integral, everything is here. So, I just need to find out how does it behave? So, what is the first term? First term is 0, what is the second term? X. So, it behaves like 2 by root pi x. So, what will be the next term? What is the order? So, next will be, so you just x is small, right. So, you just need to expand this because you are looking at this function for small x. So, this y has to be also small, right. So, you just expand this in this. So, it is like y minus y 1 minus y square plus y to the power 4 by 2, and you just do this integration. So, first is this one. So, this is equal to this plus second is x cube, right. So, now given this object, so you can see how does this probability behave for large time. So, if time is very large, how does this probability behave? This argument is small, so it should be linear in that argument, right. So, in time how does it behave? So, that goes like 1 by t to the power half, right, 1 by square root of t basically, right, as t going to infinity, right, because when t is large, this argument is small, argument of the error function, and we saw that argument of the error function when it is small, it is linear in x. So, linear in the argument. I have not put this whatever prefactor x 0 by square root of 4d and then this thing. So, but this is how it behaves, right. So, it says what? So, if t is very large, this probability goes to 0, right. So, it goes to 0 as 1 by t to the power half. So, therefore, what is this object at t infinity? So, that is also you just put it from here, t when t is infinity, that guy is 0. So, what is this object? Right, as x 0 t going to infinity. So, this is equal to zero, right. It goes like 1 by t to the power half, or even if you look at this guy, the argument becomes 0, and when the argument becomes 0, error function becomes 0. So, when t equal to infinity or realize, it goes to 0. So, ultimately this becomes 0. So, what does it mean? So, it will eventually get absorbed. So, it does not matter wherever you start, eventually it will get absorbed, right. So, it says, so eventually it will get absorbed mean it will eventually come back to. So, you start from somewhere, eventually it will come to the origin, right. So, that is like the return probability, it will just come to the origin. So, in one dimension, so I think Abhishek is going to do this thing, so that, so in one dimension you see that it is eventually this particle just gets killed. So, that is also true in 2 dimensions, but 2 dimensions now when you look at the continuum thing, then you cannot put a point, because you know that if it is a point in 2 dimension, if some trajectory, it will never going to cross that point, right. So, you have to put a small region around something, and in 2 dimension you can again show that basically it will again come back. But for higher dimensions like 3 and above, what you will see is that this guy even at t going to infinity, it has a non-zero value. So, there is a small probability, and that probability increases as you increase the dimension. So, there is a probability that actually particle does not visit this any particular site,
So,
right.
so this, so here it was just x equal to 0 in 1D.
Yeah.
So in 2D, is it going to be the?
So you just put a region, basically some region. So when Abhishek is going to do, he is going to do it. So when Abhishek is going to do, he is going to do it on a lattice. So then it's a well defined problem, because you just ask what is the probability that it just comes back to origin or some point. But if you do it in continuum, of course you cannot put a point, because it's not going to come to that point. So you have to just put a finite region.
So it's a finite
Right.
region or infinite? So it could be also infinite.
No, it's a finite region, but that, yeah, and then you ask what is the probability it does not come back to the finite region. So that finite region can be infinite. For example, you can ask in higher dimension, what is 3 dimension, what is the probability it does not come to one of the whatever quadrant, or whatever the one of the. So that region can be infinite. So D is, it again comes back. So D equal to 2, it comes back, right. So above D equal to 2, it does not come back. D equal to 3 and higher, it does not come back. So
Equal to 3, let us say I start 3 dimension.
3 dimension, you
Let's say
put
it's
some
vertical somewhere. Let's say I define this xy plane.
no, not, I guess, I think even xy plane should be fine, but okay.
Even xy plane it doesn't come.
I think it should be fine, even xy plane, but let us look at a finite region. So you just 3 dimension, you just put a finite region and ask, okay, what is the probability that it does not come back to this region. So you have this thing. So it will not come, there is a finite probability that it will not come back. That will of course depends on the volume of the region. So if you keep increasing the volume, it will, okay, this probability will keep on decreasing by some scaling way, right. Yeah. So maybe like if you just scale it to the volume, in the limit volume goes to infinity, probably yeah, that probability, right. So there will be some scaling relation. So okay, so this basically in 1 dimension and 2 dimension, this Walker always comes back. So this is called recurrent, it just keeps coming back, and higher dimensions is called transient. So it does not come back, it is just, so there are reason it may not even visit, and that's intuitively basically what happen. In 1 dimension you have less space to explore, because see, you just go left and right, you keep doing that, at some point you have to cross some point. 2 dimension you have more space to explore, so you have lots of space to avoid, but 2 is still not large enough space, so you always come back. But if higher dimension, so you have lots of space to explore, and I mean you keep exploring new and new space, but then you may not even basically come back to where you started. So this one, yeah, so 2 dimensions, yeah, let's look at this. I think so this would behave like, yeah. Okay, I will tell you later. Yeah, okay.
So the problem will be the same as, so here you have some probability of going to right or some probability of going to left.
Yeah,
So take the degree.
yeah,
Then you could also include some probability for staying there also, right?
yeah.
So if you, so this problem is it?
No, that should not change the scaling behavior. Go left, right and staying, that should not scale. So that will, as Abhishek said, that will change the diffusion coefficient, but that will not change the scaling behavior.
So will that give the same result as 2D, because in 2D also it's a similar thing.
Yeah.
So if you draw this,
Huh?
line, 2D if you ask the question,
Yeah.
that when it will cross x equal to 0. So let's say
See, if you put x equal to 0 line, so that's like a 1D problem, right?
my space is x and y.
I know, but if your space is x and y, right? If you just ask what is the probability it does not cross this line, so that effectively like a 1 dimensional problem, because all you have to look at is you have to x and y, and you have to look at this is y, this is x. So you have to look at the motion of the y coordinate.
Yes, exactly.
So that's a y 1 dimensional problem. Yeah.
So that will be the same result
As the 1 dimensional problem. Yeah. So similarly, yeah, 3 dimensional problem, if you say that okay, what is the probability it does not cross one full plane, so that's like a 2 dimensional problem, so that will of course cross, right?
So now
Yeah.
making this
that changes this thing, yeah. But I think you can still have a infinite region, but it is not the full plane, but you can have some funny infinite region. It just okay, it starts from somewhere and probably just goes all the way there. Yeah, I think there, yeah, it's still probably 2 dimension, of course it will cross, but if you look at a higher dimension, if you just make it a solid angle and say that okay, what is the probability it does not cross the solid angle, I think there is a finite probability, but okay, I might be wrong. Yeah. Yeah, so this one, yeah, I think this your answer basically Abhishek is going to yeah, tell you how it behaves. It's basically easy to see in this. Yeah, so Abhishek is going to. Yeah. Okay, so now, let's. Yeah.
When you calculate the probability of reaching to x equal to 0,
Yeah.
here in the calculation there is nothing special about x equal to 0.
Yeah.
So that means each and every particle visits each and every point eventually.
Yeah. So that's why it's called recurrence. So it just there's nothing special about x equal to 0. So basically, eventually it will visit all the space, right? But it will take more and more time, right? Because if this point is, if you start from x0 equal to infinity, it will take of course infinite time to visit this thing. But in a if you start from finite one and x equal to 0, you ask somewhere what is the probability that it does not visit. Yeah? So it's the same. So this from where you start, it just comes from this object, right. So here if it goes to infinity, that goes to infinity, then it becomes 1. So just if you start from the infinity, it will always survive, right, in any finite time. So this starting point, or that basically you should just take as the difference from the point and where you put the observer, right. Yeah. So now, yeah, so there is one more probability which is related to the survival probability. So that's called the first spaces probability. So that means, okay, so that let me just define it more clearly. See, if so, this is the probability that it does not cross the origin, right. So the complement of this is basically those paths which cross the origin. So, because the path either crosses the origin or don't crosses the origin, right. So 1 minus this is basically the paths which cross the origin. So now, so you can define something called first spaces time. So you ask, so if you start from t some point x0, so you have seen, so when is the first time it this thing crosses the origin, right. So this is x equal to 0 again. So f, so this is now a probability density in time given x0 dt. So this is basically the probability that the the particle crosses origin between time t and t plus dt for the first time. So for example, this one, so we look at this again, it might cross at some point. So this is the time, right. So if you take some other trajectory, if you take it some other trajectory, so for that trajectory, that is the first spaces time, right. So this time is the first spaces time, and you are looking at what is the distribution of this time. So this is the probability, so that makes the density, right, probability density. So, what is the distribution of those times? So, that time you can write in terms of this guy. So, that suppose some you want to ask what is the probabilities which crosses this one. So, what contributes to those trajectories? So, this basically this particle which did not survive within that range, right, got killed. So, if particle got survive up to there, those are not going to contribute. So, if particle survive up to there, so that is not going to contribute. So, those are the particles which did not survive within that range, right. So, what are those particles? So, what is the probability? So, that probability is the difference in the survival probabilities, right. The particle which survives up to basically did not get survive up to within that, right. So, what is this? So, this x0 t, so that is the probability that the particle survives up to here minus s of x0 t plus dt. So, that is the probability that the particle survives up to t plus dt. So, then this difference must be the probability which the particle got killed in between this thing, right. So, that is the those are the trajectories which cross the origin at that point, right. So, that is this probability, and that basically if you just if delta t is small, because this is, so what is this? So, f of t x0 is basically minus del del t of s of x0 t, right. So, that is like the just like a derivative of this object, no, if you just divide it by t and take delta t going to 0. So, this anyway in the delta t going to 0 limit, right. So, this is what you have. So, let us calculate that. So, you know this guy. So, you calculate. So, what does it give? So, this is equal to, so if you take a derivative of a error function, what does it give? So, that gives you a Gaussian. So, let me just write down the answer, you just verify later. So, this 0 by square root of 4 d t to the power 3 by 2 e power minus x0 square by 4 dt. See, one just this square root of 4 dt comes from just the Gaussian, and then 1 square root of t comes from the you have to again integrate this guy, right. So, that basically if you just see that, okay, if you just look at this square root of t, if you differentiate it, it gives you t to the power 3 by 2, right. That just comes from the derivative of 1 by square root of t. Okay. So, that is the answer. So, that goes like t to the power 1 by t to the power 3 by 2, right. So, what is this object? You can't see here, I guess. So, what is this object? F of t x0 dt 0 to infinity. So, that is, you can in fact just look it from here, right. So, what is this guy? S x0 t equal to infinity, right. So, that is equal to 1. So, that is basically same as saying that, see, this is the probability that it comes to the origin for the first time at time t, and you are integrating over all time. It says that, okay, that is same as the probability that it comes back to the origin. So, that is same as putting t equal to infinity here, right. So, that is again this is true in one dimension. So, if you look at the first space's probability, integrate over it, this will be 2 dimension, but if you do this integral in 3 dimension, so this will be something less than 1, right. So, for 3 and higher dimension it will be not completely normalized probability distribution, right. So, that says that basically there are some path which does not comes back to origin, right. Okay. So, this is the first species probability, but now
So the x is mod x naught.
yeah, so x is mod x naught. Yeah. So, I am just thinking x is positive, but if you just take it's just mod x naught. So, now that is fine. So, now you have a probability density which is this. So, how does this function look? You have seen this kind of function, right? How does this function look? Right. So, suppose I want to plot this function t f t x 0. So, how does this function look? So, let us start from the other side for large t. So, large t is easy. So, how does it look for large t? So, for large t this becomes 1. So, it is basically this one, right. So, it just goes like something. So, this goes like 1 by t to the power 3 by 2, that you can even guess directly, because what we are doing is just the derivative of this one with respect to time, and for large time this is the answer. So, if you take a derivative minus of this thing, so that gives you t to the power 1 by t to the power 3 by 2, right. So, this is this behavior. So, now when t goes to 0, how does this function look? So, this function goes to Dirac delta function. It goes to 0, okay, at t equal to 0, this is 0. That is clear, I guess, right, because you are asking that if you start from somewhere here, what is the probability that it crosses the origin at 0 time? That is of course 0, right. So, now within this one, how does it go? Okay, it is 0 here, it is going somewhere. So, it must be something like that, right, and then it comes to 0. So, how does this function comes to 0? So, which term contributes near t equal to 0? This exponential term, right, and you know how does this function behave near t equal to 0? You have seen this function, right, exponential of minus 1 over x, right, near x equal to 0. So, it has some property, right. What kind of property it has? So, it is called some kind of singularities, right. If you read these singularities in your complex analysis, so this is one of the singularities, right. So, it is called essential singularity, right. So, any derivative of this function is 0 at x equal at t equal to 0. So, basically if you look at a function something like e power minus 1 over z. So, any derivative of this function near z equal to 0 is 0, right. So, it does not matter if you put any powers of any powers here. So, this is stronger than this divergence. So, this guy is going to go to 0, but if all derivatives are 0, then how does the function grow? It does not grow, right. If all derivatives are 0, the function does not grow, because if you look at a function, let us look at x square. So, how does x square go? So, x square becomes something like that. How does x to the power 4? So, x to the power 4, it has a flatter one here, x to the power 6 it is even flatter, and they all, right. So, if all derivatives are 0, it is very flat here, right, and then of course, when you go away from 0, so this effect goes down. So, basically for t equal to 0 it is like that, and then it just grows something like this, right. So, it has a very slow growth, and this one, now you just think of this problem in terms of the, so it gives you a scale here, right, some kind of scale here where this function is flat. So, what is that scale? So, that scale is roughly t goes like x square by 4d, right. So, that is the scale x 0 square by 4d. So, that is roughly the scale where if t is much smaller than x square by 4d, then that whole thing is basically small, right. So, now, so that gives you a scale basically. So, now just think of this problem in terms of your discrete problem. It is a random walk, it does random walk on a lattice, it starts from x 0, these are now discrete points, it is like a, instead of this now it is on a lattice. So, you start and you start from some point x 0, and at each time step it just goes by 1, either up or down, and ask what is the, when is the first time it crosses this point, can that point time be 1 in terms of the discrete time? No. So, what is the time, minimum time? So, it has to be x 0, right. So, if you plot this probability, what you see is that from 0 to x 0, so if you like look at this f now in terms of the discrete one and x 0, so this is your n. So, this has to be completely 0, and then okay, it will go somewhere, and for large n it will basically follow this one, right. So, this is basically just similar to that, right. So, here it is completely flat, but since it is a continuous, it you can in principle go like you can just one thing go, but it is a very small probability of going there. Okay. So, I think I have half an hour. So, let us do now, let us try to derive this one. Okay. So, basically let us try to solve that equation with the boundary condition. Okay. Do you have any questions before that?
So that gives the kind of characteristic velocity. So
There is no velocity here.
yeah, there is no velocity.
Yeah, it is just a characteristic time.
Yeah, there is a velocity.
Yeah.
So but if you think of that x 0, whatever you get.
Yeah,
from that,
yeah,
that-
yeah,
So you already have an x 0.
yeah.
And you get a time scale from that.
Yeah, so time scale is basically x 0, but then it also depends on the diffusion coefficient, right? How fast it goes,
Yes.
right?
So that time scale like up to which this is like.
It's some okay, it's just but okay, this time scale, yeah, this is like a, it's a rough time scale. So
Yeah.
that time scale just comes from that, in fact, that one, right?
Exactly.
Yeah.
So that let us say is t naught.
Yeah.
Then x naught by v naught, so that gives some kind of.
There is no velocity in sense because it's, see, x goes like square root of t, so you cannot divide a time and call it a velocity, right? Yeah, yeah. So there is no velocity, right? So no, I mean, it's not right to think in terms of velocities,
Yeah.
right? See, velocity you say that when something is ballistically moving or something, but here x grows like square root of t,
Yes.
so then you cannot divide by a time and say that this is some kind of velocity. Yeah.
Yeah, but if means there is an allowed path which is like it goes in one direction.
Yeah,
That
yeah.
is an allowed.
Yeah.
So that has some kind
But
of
that
time.
path can be in a very small time, it just one, because
That's also allowed.
yeah, because your jump has a continuous distribution which goes from minus infinity to plus infinity,
Yes.
right? But it's, let us say you have a Gaussian distribution which goes from minus infinity to plus infinity, but the weight is very small, but there is a finite weight, right. So, there is a finite weight that you go from here to here any small amount of time, but that weight becomes smaller and smaller when you reduce the time. That is exactly this one, right, e power minus x square by 4 dt, forget about this thing, right. So, that is for anything there is some time, there is some probability that you will go from here to there, right. Okay. Yeah. So, yeah, so this velocity, yeah, one should not think, I think as a velocity. So, okay, before now deriving this, let me just make some analogy. Let me just forget about whatever I have done here, and let me just make analogy between this equation we have written down. So, that is namely del p del t is equal to d del square p del square here, and some other equation you know in some other context, right. So, this is okay. Diffusion equation. So, do you remember any other similar equations you have? Huh? But that is the same equation. Yeah? Wave equation is not same, right? Huh? But that is how we arrive at this equation. Schrodinger equation, right? What is the Schrodinger equation? So, quantum mechanics. So, what is the Schrodinger equation? I h cross del t of psi, that is equal to free particle. So, we are just talking about free particle. Huh? Minus only grad square psi, or let us finite mass, all full quantum mechanics. So, h cross square by 2m So, these two equations they look more or less same. All right, let us make it even better. So, that take the minus sign on this side, and then I take it down. So, that cuts the minus sign. So, what is it? Del I h cross goes where? Here. Psi is equal to h cross square by 2m del square psi del square. So, now it is the same equation. This equation and this equation, they are same. You have to just do some mapping. So, what is the mapping? So, take p here x t, that you take it to psi x t. So, this mapping is only for free particle, right, because we are just doing for free particle, right. So, you will see that this mapping will be modified once you have a external potential. So, what is the other mapping? D here, that goes to h cross by 2m, and time here goes to I by h cross time. So, here if the time is real, here basically time is imaginary, here if the time is imaginary, time is real, but that is like a, so it is just a mathematical analogy. And so, this one is called weak rotation. So, imagine that time is some variable in the complex plane. So, that how do you go from here to here? By rotating by just pi by 2, right, in a complex plane, plus some rescaling, right. So, this one is called weak rotation. Okay. So, now given this, now you know how to actually solve a Schrodinger equation, because that we have done, we have taken lots of courses on quantum mechanics. So, we know how to solve Schrodinger equation for various potential, etc., and free particle is very simple, right. So, now so let me just go a bit ahead and let me just write down the Schrodinger equation in more in the operator form without just putting this any particular representation of the Hamiltonian. So, how does it look? So, it looks like I h cross del del t of psi is equal to h psi. So, what is the solution? You know the solution. So, if I solve this psi at time t, so that is what is the answer in terms of this operator? I can write down the solution. So, that is e power minus, so I becomes minus I by h cross h t psi of 0, right. So, that is the formal solution of that equation, right. So, this psi is in this position basis. So, we want to write down this psi in the position basis, right. So, what do you do if you want to write down psi in the position basis? So, you just put a, right, this is how you write down in the position basis, right. So, this is equal to x e power minus I by h cross h t psi 0, but that one I can again insert a basis. So, how do you insert a basis? So, that just becomes, I just put a complete basis x e power minus I by h cross h t x 0 x 0 psi 0, right, just this thing. So, this you can now write it down. So, it says psi of x t is equal to minus infinity to plus infinity dx 0. So, let me just write down this guy first. So, that is psi of x 0 0 and this object let me just call it g x t x 0 0. So, where so, where g of x t of 0 this is equal to x e power minus I by h cross h t 0. So, that is just the quantum mechanical propagator, right. So, this propagator you get in quantum mechanics. Right, and if you want to write down in the position basis, so this propagator satisfies some kind of differential equation. So, what kind of differential equation it satisfies? So, it just satisfies this one. So, I h cross del del t minus h in the position basis, which is basically this guy. So, x on this guy x t x 0 0. So, that gives me I h cross delta of x minus x 0 delta of t. So, it just says that okay, for all time t greater than 0 basically this is equal to 0. So, this is similar to basically the diffusion equation, right, the diffusion propagator satisfies. So, because we wrote down this yesterday probability of the diffusion equation in terms of some propagators, right, and we see the propagator is basically the one which satisfies this diffusion equation with this initial condition where x start from x 0. So, this is similar. So, in the quantum mechanics this guy, this wave function you can written like this, where this propagator satisfies this equation, right. So, this h x in general is minus h square by 2 m plus some potential, but here we will just consider the case where potential is 0, right. So, this is just quantum mechanics whatever you have learned so far, right. So, I am just going through very fast, that is it. So, now this propagator, you know that you can also write down in quantum mechanics this propagator in terms of the path integrals, right. So, what is this in terms of the path integral x t x 0 0. So, this is equal to basically, so quantum thing you can just think of its path. So, which goes from at x 0 is equal to 0 and x at time t is equal to x tau. So, that means basically lots of integration over all times, right. So, this means basically if you just think of it as time in some discrete manner. So, it basically says that the integration over this variable x it all those times. So, this is the short form for that, times exponential of something, exponential of what I by h cross 0 to t tau. This is just the Lagrangian, right. So, I am not going to use this, do not worry. So, this L x 0 x tau. So, this is just the Lagrangian. So, this is Lagrangian, and for free particle the Lagrangian is half m dx d tau square. So, that is the free particle Lagrangian, right. It is just the kinetic energy. So, half mv square, right. So, that is the Lagrangian. So, this is this thing. So, now given this you can yeah. Have this equation del p del t is equal to p Lx square and corresponding path integral, right. So, we enter, so path integral basically says that if you, so there is some path and what is the weight for that path, probability for that path. So, what kind of path we have? The path is very natural in here, right, because this just we have been drawing those paths. So, you start from some point, it just goes. So, these are these paths, start from some point, goes. So, these are these path, and you want to find out what is the weight for a given path, right. So, if you know the weight for a given path, so you can compute other things, because to compute some expectation values you need the weight for that path and whatever the observable for that path, right, and then you average over those. So, how are you going to do? So, we have shown that this guy satisfies some kind of equation. So, what is that equation? Dx dt is equal to square root of 2d eta t, right. So, where eta t prime is equal to delta t prime and eta t is equal to 0. So, now these etas are Gaussian random variables. So, only random quantity here we have is this guy, right. So, this noise are the random variables. We know the weight of this noise. So, this everything has to come through this one. So, now for a given path, this path is generated by some sequence of noises, right. Basically given this noise, let us say eta t1, eta t2, right. So, just think of it like a discrete time, but in, so basically just a set of etas where tau goes from 0 to t. This set of etas basically gives this path. So, what is the distribution of a given eta? So, let us skip that one. So, what is the distribution of a given eta? So, P of eta, I said it is a Gaussian random variable. This one I have already taken out here 2D. So, what is the distribution? This is just 1 by square root of 2 pi e power minus eta square by 2. Right? It is a Gaussian random variable with 1.
That is your choice.
That is my choice, right. So, that is, so I am assuming that these etas are basically drawn from a Gaussian distribution, right. So, now given this for each eta, so what should be the huh? No, variance is 1, I put this delta. Yeah. So, now when you go to this path integrals, so you should just think of it basically like a sequence of this times, small times, so discrete times. So, finally, we will again make it continuous, but just think of it, you have to do this integral. So, you have just what is the meaning of this object? These are some integrations, right, at x's. So, just think of it, so your time is continuous, but just think of it, just you are just discretizing in very small interval some epsilon and just doing this integration over these different epsilons, just mentally just think about it. Okay. So, now during each one, so I have, so this basically the now the weight of this is just 1, because I have just integrated this delta function, right. So, this is just the unit weight on everything, I have just put it here, right. So, now, so that should be proportional to, I forget about all these proportionality constants, right. So, that should be proportional to, because that proportionality constant I can just find by normalizing this guy, right, because this probability should be normalizing, should be proportional to exponential of minus half 0 to t eta square tau theta, right. So, these are basically again this, because these are independent. So, these are again product of these probabilities. Now, product, if I take it to the exponential, it becomes sum, and that sum again I have made it the integral, right, because these are just so this means eta at all these times, right. So, that is this product. So, that I made it a, so it is the product of this exponential. So, product of exponential is same as the exponential of the sum of this argument, sum over time, and that time I just made it a integral, the sum I just made it a integral, right. So, this one is in terms of the etas. So, now given in terms of the etas, I can, because there is a connection between eta and x, so I can write down the weight of this path. So, from this one, so I want to write down weight of this path, right. This basically, this means basically the whole path. So, that weight is, when you go from one variable to another variable, there is a Jacobian for the transformation. So, that will come here times exponential of minus half. What I have to do is just use this equation, replace eta by this guy. So, if you replace eta by this guy, so what you have, so this half and then there is 2d, so it becomes 4d 0 to t dx d tau whole square, and this Jacobian, so you can show that basically when you go from here to there, so the Jacobian is 1. So, that Jacobian does not depend on the path for the free case, right. So, when you have potential, that will change. For the free case, the Jacobian is basically independent of the path. So, it is just some 1 or some number, so that you can just put it in the normalization. So, this is what you have, right. So, now you see that this and this in fact very similar, right, because if you just do this transformation, I have, so you can again write this one just putting L, this one you can just write this one in terms of that by doing those transformation I have shown between T and I by H cross T, D and H square by 2m, right. So, you can say that these two are basically similar. So, this one the propagator, if you, so this one the propagator is this one, right. This is equal to this. So, therefore, this is equal to x e power I by h cross t is just the minus h t times x 0. So, this is just the quantum mechanical Hamiltonian now, right, because so you can write down this process in terms of this quantum problem. So, now we are going to use this. So, this one actually if you just take this one and okay, you can actually do it immediately, right. Now, you know this. So, let us do this problem free particle, right. So, what is this one x, you write it in k basis. So, what is the basis you should take if it is a free particle? It is the momentum basis, right, this because it is just e power. So, you just put in k basis. So, this is k e power minus h t k prime x 0, this is equal to dk prime, but this one is diagonal in k basis, right. So, then this one integral goes away. So, this is just the dk and just I just put k prime equal to k. So, now you know all these terms, right. So, what are these terms? So, this is my propagator, right, g of x t x 0 0, this is my propagator. So, what are these terms? So, this one you know, right. So, this is okay, you cannot fully see here. So, let me just write down there g of x t x 0 0. So, this is dk e power I k x. So, what is this one? What is h? H square by 2m. So, e power minus h square k square by 2m times t, but h square by 2m we have mapped to something. So, d, right. So, it is just d k square t and then that one e power minus I k x naught, right, and you integrate over k. So, you have to normalize properly. So, okay, let us just put it this guy. So, you have to normalize properly. I think this is normalized, I guess. Okay, you have to just put the normalization here. So, this it is not normalized, but otherwise you just put this yeah square. So, if you you just put square root of 2 pi here and square root of 2 pi here, right, that normalization. So, then so I think this is the normalization, no. Okay. That is the normalized wave function, because if you do not have this one, if you integrate it, you should just get a delta function 2 pi times the delta function. Right. So, now this is what we got yesterday in fact, right. So, did you do the integral? You are supposed to do this integral yesterday, and the answer was 1 over square root of 4 pi dt e power minus x 0 whole square by 4 dt. So, this is equal in fact, because these are normalized things. This is So, now, what we have got is basically whatever we have derived yesterday, right. Just by knowing this quantum problem, we didn't solve anything, right. We look at this quantum problem, we know the quantum problem because we have been doing it free particle quantum mechanics, everybody knows, right. So, just put it there and we got the answer. So, you can use similar trick to now solve the problem with this absorbing boundaries, right. So, absorbing boundaries is what? So, you want to look at all paths which does not cross the origin, right. So, how do you do that? Given this propagator, so you know this propagator, yeah, given this propagator, now how do you do that? Let me just write somewhere here. Okay, this one I do not need now, right. So, how will you do that? So, you look at only those paths which does not cross the origin, right. So, you want to find out now this guy P of A x t x 0 0. So, this is what you want to do, right. So, let us just put it proportional to, okay. So, this guy, for this guy, so basically you look at all the paths which goes from x 0 to x without crossing the origin, right. So, this is, so what are those paths? So, let us first look at the paths x tau without crossing the origin. So, that is proportional to, what is the weight? So, weight is same, e power minus 1 over 4 d 0 to t dx d tau whole square d tau. This, so now, so this is the weight of full path, but now I am only fixing these two endpoints. So, I do not care how it went in between. So, I just integral over all these midpoints. So, that is in shorthand written like this. So, this basically integral over all midpoints, keeping x here equal to 0 and x t equal to x. But if I just do that, so that will give me all path which goes from x to x 0 to x. So, that is basically this one, but I need to restrict the path, right. I need to, so that means, so I have some kind of theta functions, right. So, that is again product of theta functions. So, it says that all these path at all time does not cross the origin, right. So, it is basically something like, okay, let me just write something like that, product over tau theta of x tau. So, all paths basically stays on positive. So, whenever this at any time this becomes negative, so that gives me my weight 0. So, these things should give me this one. So, in turns that guy, right. So, this one is more or less the same except this guy. So, this one is, if I just take it a log, right. So, it is always, see, these products are not very nicely defined, right, but sums are nicely defined because sum I can just write it as like an integral, right, but products, okay, I do not know, okay, this is some this thing. So, I can just write it as sum. So, I just take an exponential of it. So, what does it give? So, this gives me exponential of sum over tau log of theta of x tau, right. So, what is theta of x tau? Log of theta of x tau. What kind of function is this? Log of a theta function, right. You know how theta function behave. So, how does theta function behave? 0 and 1, right. Huh? So, it is minus infinity and 0, right. So, 0 gives me minus infinity and 0. So, if I just put it inside, so it basically says that you have a hard wall. So, this minus sign, if I just take care of it, it becomes this thing. So, it is now a quantum Hamiltonian with a potential, right. So, that potential is basically something like that. So, it is an infinite potential at x equal to 0, this is infinity. So, this basically correspond to a Hamiltonian now, which is minus h cross square by 2 m del square del x square plus v of x. So, what is v of x? So, v of x is infinity for x less than infinity and 0 for x greater than infinity. Sorry. So, this is this potential. It says a hard wall and quantum mechanics problem. So, you know this one, right. So, what are the eigenfunctions for this problem? So, free eigenfunctions I know. Now, for this one, what are the eigenfunctions? So, if it is a hard wall, it has to vanish at the wall. So, therefore, so these are sine functions, right. So, these normalized eigenfunctions are just sine functions. So, like x k, so these are sine functions. So, what is the normalization? 2 by just 1 minute, yeah, I'll yeah, okay. So, sine k x 2 by square root of 2 by pi and k greater than 0. Okay, I can just take k greater than equal to 0 because this wave function either k greater than 0 less than 0 is just the this thing, and you deal with the mod of the wave function. So, it does not matter, right. Okay, anyway, it is one side is a boundary. So, it is just a positive wave function, a positive k, yeah. This one, see, this is theta functions, right. So, theta functions are like what? If you just take a log, it is same as exponential of log of a theta function, right. So, now how does the exponential of a log of a theta function behave? It is just 0 and minus infinity, but that minus sign basically just if you just take properly this thing, put it inside. So, that becomes this potential. So, that potential becomes the plus sign, right, because see, this I have written in terms of this, but you should write in terms of the kinetic energy term minus the potential energy term, right, when you write down the Lagrangian. So, that corresponds to a potential which is plus infinity and 0, right. So, this is the this thing. So, now I want to write down this one. So, this is should be easy now. So, this is same as the propagator. So, what should that be? So, let me just clean this and clean this. So, this what are the eigenvalues? So, this is what I have, right, with a now with a absorbing boundary. So, that is same as P, right. So, what are the eigenvalues? So, eigenvalues are same, right, because it is a free particle only. So, what are the eigenvectors? So, these are those. So, that gives me 2 over pi. So, this goes from now 0 to infinity, 2 over pi. So, I have one sine of k x and sine of k x 0, and I want to do integral over k. So, this integral you have to do, right, this I will leave it to you. I will just give you a hint how to do this integral, because we have just done a similar integral. This sine of x is what? E power I x plus e power minus I x by 2 I, right. Right. So, yeah. So, if you just use this one here, so then it is like the similar to our old integration. Old integration was this e to the power I k x, e to the power I k x, yeah, yeah.
So, that is 0, right? 0 to infinity, the dk integral.
0 to infinity, yeah. Yeah.
Minus is already taken.
Yeah, minus is already taken care of in the wave function, right. So, that is 0 to infinity. Yeah. Right. Yeah. 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 So, if you do this, so what you should get is basically the same thing we have done before. You can actually, yeah, so that is same as whatever PA XT x00, that expression you will get before. Okay. So this mapping is basically just a very nice way of because you have solved lots of problems in quantum mechanics and with very complicated potentials, right. And once you know this mapping, you can just take these answers and use it here, right. Furthermore, this writing down these probabilities in terms of this path even has more use, because sometimes you want to write down, see all these observables we are writing in terms of just 2 points, right, except that okay, survival probability. But sometimes you want to write down observable in terms of this path, then you need the weight of the full path, and this is a useful way of writing down. So once you write it down that in terms of this path integral, so you can always look what is the corresponding quantum mechanics path integral problem. So once you identify the quantum mechanics path integral problem, so immediately you can write down what is the corresponding Hamiltonian. So once you write down the corresponding Hamiltonian, you know what is the quantum mechanics Schrodinger equation, and you just look at the solution of this one and just put it here, right. Yeah, okay. Yeah, so I will just stop it here.